Okay, so before we start, I would like to make an announcement which had to make a change in the schedule for the last week. The last lecture and the last exercise, we swapped time, so we will have the exercise on Thursday and the lecture on Friday. And it's a little bit non-standard time for the lecture. It starts at 2 o'clock, not 1 o'clock, or 2:15 actually, and that has to do with there's apparently a course evaluation meeting, and then I'm not allowed to use the 1 o'clock slot there. But anyways, it should be on Canvas and all these things, and time edit is always updated. So, and time edit is the prime source of the information, so all other information comes from there. So if it's a conflict, time edit is what is current. Okay, and also before we start with today's lecture, which is about multiple access, we did not quite finish the material last time with that lecture. I looked a little bit at that material, and it's not super difficult, so I will, in the interest of not delaying the course further, I will leave that for you to read. And then please come back to questions with to me or Shoaib if it's something unclear. And if we find time at the end of the course, perhaps I will do a review of that material also. But in the interest of not losing time and spend time on the more difficult parts, we will just continue today with multiple access. So what is multiple access? Well, it is, why is this not working now? This is not my day. Let's see. So multiple access communication is about how different transmitters are using share a common medium. So if we have here what's called as stations here, STA stands for station. Let's see if I can, no. There's something wrong with this pen today. That's unfortunate. But anyways, we have these stations. You can think of these as transmitters, users, or some type of nodes which are attached to a network. And the network here consists of a common medium which we call the channel. So you can think of these as being your Wi-Fi devices, and this is then the radio channel that is connecting everything together. So we haven't talked about this problem before. We just assume that we can transmit data over a channel, but all channels are in practice at some point shared among different users. So there are different approaches to this media sharing, and if we take all the multiple access methods we can think about, we can broadly divide them into two things, something which is static and something which is dynamic. And with static, we mean it doesn't change in time, or at least it doesn't change very often. While dynamic will change often, perhaps on the same, on the time scale of a packet or several packets and so forth. So if we look at the static ones, which we will talk more about later, the main method for this is something called channelization. So basically that means that we partition the medium into channels, and then we allocate channels to users on a very long time basis. So think of FM radio, for instance, or TV broadcast. You know that P1, the program P1, is at a certain frequency here in Gothenburg, and it's been like that for a very, very long time, and will continue to be that for a very long time. So then P1 has an exclusive use of that channel for a long time. TV broadcast is also something which is, a common example of this. The dynamic one, which we will concentrate more on in this course and also today, can be divided into two main classes, and one is coordinated and one is random. Or coordinated or scheduled access means that we plan how people or nodes are using the channel, so in a structured way. Random access is more loose coordination, or sometimes absolute very little coordination, where users use the channel a little bit in a randomized fashion. And there are some, actually some advantages and disadvantages with these methods, and we will talk more about them as we go along. In the coordinated one, at least, it's careful coordination, and there are two main things that we will talk more about today. Later, we will not talk so much about them today. And an example of a system that uses scheduled or coordinated access is cellular systems, so like 4G, 5G, and so forth. Random access, more loose coordination. Basically, we listen to the medium. If the medium is available, or then we send. And if there is a collision on the medium, then we have to take action to recover from this. An example of this is Wi-Fi and Ethernet, and schemes like that. So, when selecting a medium access control method or strategy, what comes into play here? Well, of course, we would like this to be good in some sense. So what is meant by good? Well, first of all, where is medium access control? Where is this in the protocol stack? Well, at the bottom, it's the physical layer, and on top of that is the data link layer. And typically one divides this into two parts. One which is called medium access control, which is the layer just above the physical layer. And then we have the data link control. And the data link control is responsible for these retransmission protocols, framing that we did not talk about but was on the last lecture, flow control, which we haven't talked about but was also on the last lecture, and so forth. So this one has to, the data link control has responsibility for these things, but today we will talk more about medium access control. Okay, so it's the layer just above the physical layer. Okay, so sometimes it's called a sublayer. And considerations when choosing a method or a protocol for this MAC, what do we want to do? Well, we want to have ability to handle the traffic, and there are different types of data traffic. It could be steady or bursty traffic. It could be short or long messages. So whatever data comes from the data link layer down to the MAC control, it could be like bursty, steady, long packets, short packets, right? So of course our MAC layer should be able to handle that type of traffic. So different MAC layers have different advantages when it comes to this. Some of them are very good at handling just fixed packet lengths, and some of them are more flexible. We should also then provide some type of quality, and quality can be measured in many different aspects, but one is the delay it takes for a packet to go over the medium, the shared medium, and then also the variation in delay, which is called jitter. So let's see if I can. So this jitter is variation in delay. We also want to be fair in the sense that we would give all stations which are attached to the medium an equal share somehow, or fair access to the channel. So not one station takes the medium forever, so to say. We also need scalability, and scalability means handling many stations, that is many users, and or a lot of traffic. And then we're interested in providing all these things with some type of efficiency, because we would like to use the physical layer in an efficient manner. So again, as we talked about the ARQ protocols previously, we would like the ARQ protocol to handle its lower layer in an efficient manner. Same thing goes here. So the MAC layer here should use the physical layer in as good of a way as possible. So this is known as coordination efficiency. And then sometimes we also would like to provide a quality of service guarantee. So quality of service, QoS is quality of service. And that's a broad term, and which includes things like this. So the quality could be some type of delay requirements that we need to fulfill, or some jitter requirements that we need to fulfill, some type of fairness among users. It could also be throughput and other things. So quality of service is quite a broad term here. We sometimes also like to be able to handle priorities. That is, that certain stations have more pressing needs than others, and we would like to be able to handle that sometimes. And of course, reliability and cost of equipment. Okay, so this is generally what we would like to do. So let's see what some common performance metrics in more detail here. Okay, so we talked about the frame transfer delay or the Mac-to-Mac delay, and let's call that T. Okay, so how do we define T? So we have T here. So at some point in time, a frame goes down here through the Mac layer and then over the physical layer and then up here, so, right? It goes this direction. So the time it takes from when it enters into the Mac until it leaves the Mac on the other side, this is called the frame delay or frame transfer delay. So what could cause that to be long or short? Well, it depends on the Mac layer, for instance. The Mac layer could be so that it waits a little bit until it accesses the physical layer, depending on the status of the physical layer. Or it could be like the Mac layer is such that we have to wait for a time slot before we can transmit. So different Macs have different delays, essentially. Typically, we model this as a random variable. So it has an average and then also CDF. We're sometimes interested in the, the probability that the frame transfer delay is less than a certain amount, and we would like that. Okay, so the probability of what is the delay for 99% of the frames, for instance? That's a quantiles. Okay. We're also interested in the throughput, which is the actual transfer rate through the shared medium. As the medium has a data rate, maybe R bits per second, but what is the data rate that the layer above the Mac layer experiences? So this is similar to what we did in the crew case, right? We would like this data rate that the layer above the Mac layer experiences is as high as possible. It cannot be higher than R, but we would like that to be close to each other. If we have then, what complicates things here is that we don't have just one transmitter and one receiver. Typically, we have many stations attached to this medium. Okay. So the traffic on the medium here is the data rate here needs to be shared between all the users of that medium. So if we have capital N stations attached to the medium, together they generate some load, which we denote by lambda. So lambda is the number of frames per second of length NF bits. Okay. So if the nodes together generate lambda frames per second, and each frame has NF bits, then the normalized load is lambda times NF divided by R. This was annoying. Okay. So if we, for instance, have three stations, and then we have one station which generates, say, 2 frames per second. The second node has a little bit more data, it's 4 frames per second, and the third, say, 1 frame per second. Then lambda, the total load we have, or the total number of frames which are generated in this system, which use the same medium, is simply the sum of all of these. So in this case, it would be, 4 plus, it would be 7 frames per second. And then if we have, say, 7 frames per second, and then we have a number of bits per frame, we can translate this into the number of bits per second which we would like to transmit. Okay. So if each frame is NF bit long, then the data rate that we would like to transmit is lambda times NF. Okay, and this is in bit per second. Okay. So lambda times NF is the number of bits per second that we would like to transmit, and then if we divide it with the rate we have on the medium, we get sort of like an efficiency, but we changed notation. Usually we call this eta before, but now we call it rho in this context because this is the established notation for this. Okay. So this rho, how can we interpret that? Well, it's the ratio between the total data rate generated by all stations attached to the medium divided by the data rate capacity of the medium. Okay. So a MAC then, a medium access control scheme, can support a certain rho. It can support all the rows which are less than rho max. And rho max is something which different MAC schemes have different rho max. And rho max is less than 1. And why is that? Well, it's because we cannot transmit more bits over the channel than r bits per second. So if we take the data rate that we would like to transmit and divide by r, we get a number which is less than 1. So we can think of rho max as being, we can interpret that in 3 different ways. It's the maximum supported load, or we can call that also the coordination efficiency, or we call it also the maximum normalized throughput. Okay. Maximum supported load because, I mean, we call rho the load, and then rho max would then be the highest load that we can have. Now, coordination efficiency comes a little bit from this ratio between the data rate that we would like to transmit divided by the data rate we have available. So if rho max is close to 1, then the MAC scheme is very efficient use of the medium. And maximum normalized throughput is basically because this is the data rate that we offer to the medium, and if we normalize that with the data rate that we have available on the medium, we get the normalization factor, so normalized throughput. Okay, now the transfer delay and the load are somewhat connected to each other. And essentially means that if we have a lot of load, that means we have a lot of data to transmit, and then we can have long waiting times before the medium gets available. See, that will be a little bit more clear as we go through a few examples later, I think. Okay, so the main problem with MAC, what is that? Well, it's because we need to share the medium between many transmitters. So if we have our stations here, we have station 1, station 2, up to station M. Now, all of these are attached then to this medium, and let's think about this as a cable for simplicity. And suppose that the distance from the first station to the leftmost station to the rightmost station is d meters. Then the time it takes for a signal to propagate from one end to the other end of the medium is of course d divided by the propagation speed. Now that turns out to be problematic because when we are sharing the channel propagation time is an important factor in this, and it comes into play in the following manner. So if station 1 wants to transmit something, that transmission is not noted at the other end. It takes t-prop seconds before this is measurable at the other end. And then if we want to coordinate access to this, we would like to avoid collisions. And to do that, we use the medium in order to do coordination also, not only to transmit data. So think of it as the following. I don't know if you've been talking over the phone with a person where there is a lot of delay on the line. Have you thought about that sometime? So sometimes if you talk in the good old days when things went over the satellite network, if one talked to say somebody in the, at another continent, there was a significant delay, maybe 250 milliseconds, half a second or something like that, in the delay when you talk. And when you talk, have a conversation like that, you start to talk, and then the other person, politely listens to what you say, and then answer something. Right? And then you're politely listening to that person. But if there is a significant delay here, we don't hear the other person talking until we started to talk ourselves. And then there is this collision, and then you wait, and then there is another collision, and so forth. So this coordination over a medium with a lot of delays is very similar both with humans and computers here. So this delay is an important thing, and if we take the delay and then we normalize that with the time it takes to transmit the frame, then we get this delay bandwidth product that we talked about earlier. So that turns out to be an important factor here also, and it has this mathematical definition. So A is the normalized delay bandwidth product. So it's the propagation time divided by the time it takes to transmit a frame, or the time it takes to transmit a frame is R divided by NF, or sorry, NF divided by R. So we can write it in this form instead. So this coordination of a shared medium is then problematic as A increases. So when A increases, then the maximum supported load typically decreases. Okay. So just to illustrate what is the meaning with this delay bandwidth product is that we have a medium, say, which has a certain distance from here to here, and then we can think of this as being in time from 0 to t prop. And if we then are sending frames in here and send it and picking them up here, this delay bandwidth product can be thought of as how many frames can fit onto the medium at the same time. So if we here have time and we have here TF, then TF T prop divided by TF is the number of frames that fit on the medium. Okay. So if we send a frame from one end to the other end of the medium, it will occupy a certain time, which corresponds to a certain distance on that medium. So we can think of this as we push in frames to the left and put them up to the right, and how many frames can simultaneously be on the channel here. And that turns out to be this delay bandwidth product. So the question is, how many can really fit on this? Well, it depends, of course, on the propagation time, and it depends on the data rate and the number of bits in a frame. But for sure, we can have multiple of these going over, say, a satellite links. There is no satellite link might have, I don't know, milliseconds of propagation time, and then a frame could be on the order of 0.1 milliseconds or so. When can we have 10 frames in the air at the same time, non-overlapping, right? They arrive at the receiver at different times, so we can just transmit these. Okay, so that's the interpretation of this delay bandwidth product, and we will show that the bigger that one is, the more difficult it is to coordinate the access over the medium. Any questions? Okay, so then let's continue then. So this transfer delay and load, okay, so for every max scheme, we have a maximum normalized throughput. So if we start to push data through this medium with a certain medium access control, then at some point we cannot get any more data through this. So this is the best we can hope for in throughput. But if we push the system to its limit, close to its maximum throughput, then if we look at the delay, okay, remember that the transfer delay is a random variable. So if we take the average of this and then normalize it, say, with the frame duration, then at very low loads, we basically the only delay we have is due to the delay it takes to transmit the frame, which is TF seconds. So this is the lowest delay we can ever hope for. That basically we transmit the frame immediately and it's received immediately. Okay. But then as we start to increase the number of frames that are sharing the medium, that is increasing the load towards rho max, then the delay typically goes up like this. Okay. So this is not for any particular scheme, but it's a general behavior of the schemes. And the reason for this is that we typically have to wait a little bit before we can access the medium when the medium is very busy. So I mean, it's the same thing as when you go with public transport, right? You know, from my home to the office here. That if I go when there is not a lot of traffic, then there is not a lot of delay. But if I go when there is a lot of traffic, then there is a lot of delays, and also very random how the delays are, right? Same idea here. It's just now we're talking about data packets, not buses and cars. Okay. So the transfer delay is a random variable. And the frame duration, again, TF is NF divided by R. NF is the number of bits in a frame, and R is the data rate on the medium. The transfer delay typically increases, and it increases dramatically as we approach rho max. So when we push the system to its capacity. And that's typically due to longer channel access delay. The delay before we, okay. And then rho max, what is this value here? And then that typically decreases as A increases. So if A, again, is T prop divided by TF or R T prop divided by NF, if the medium becomes longer or there are more delays on the medium, then we push this boundary to the left. Okay, so the maximum capacity, the coordination efficiency or the maximum normalized throughput decreases as A increases. We'll see an example of this shortly. Okay. Any questions? No? Okay. So let's make a toy example here. So this is not a serious medium access control scheme, but just to show how we could approach this and show some general behavior. So we have a very simple system. So we have only two stations. So we have two nodes attached to the medium. So and we have station number 1 and we have station number 2, and we have a medium like this. Think of this as maybe a cable, and it's on distance D. So the distance between station 1 and station 2, physical distance is D, and the time it takes for the signal to go from station 1 to station 2 is the propagation delay, which is the distance divided by the propagation speed. Okay. So there is some delay here. Okay. Now the medium access works as follows. A station which has a frame to transmit, what does it do? Well, first of all, it listens to the medium. Okay, so if station 1 has a frame to transmit, it listens to the medium. If the medium is idle. That is, that there is no frame currently in this vicinity. What do? It listens to the medium. If it's busy, wait, but it listens until it's idle, and then it transmits a reservation signal of duration 2t-prop. Okay, so this is sort of like a coordination signal before we actually send the frame. And it has a certain duration. It's twice times t-prop. Why we want this will be obvious later, right? It just does that now. And then it listens to the medium to detect whether there is a collision with the ongoing reservation signal. If there is no collision, then it transmits the frame. So what is transmitted from the station is first the reservation signal and then the actual frame. Okay, so this is the frame and this is the reservation signal. Okay, and this one has a duration 2t-prop, and the blue frame here has duration tf. Okay, so this is what's done. If a collision occurs, then we have some logic in deciding which of the stations that can use the medium. I will show that. It will be easier to show this in the next slide. So let's forget about that right now. But after transmission of the frame, then the transmitting station is silent for a certain time to allow the other station to come into play. So actually we have a silent period after here also. So this is the silent period before we can start again. Okay. So let's look at the timing diagram on this. So here we have station 1, which is also called A here, and here we have station 2, which is called B in this case. So and the distance from here to here is this d meters, or the distance in time between these two things is the t-prop thing. Okay. Now, suppose station 1 here, at this point in time, has a frame to transmit. It then listens to starts to listen to the channel. If the channel is idle, which it is here, it's idle, then it starts to transmit its reservation message. And this goes over the channel, and then it reaches the other station at this point in time. And it takes, of course, the t-prop to go from one end to the other end. Now, the station B is also having a frame to transmit, and that frame becomes ready to transmit at this point in time. So here station B has a frame to transmit. Station B listens to the channel, and if the channel is idle here, it starts to transmit its reservation signal, and it reaches the other side at this point in time. Okay. So here we see the problem, right? Just listening to the medium is not enough to ensure that the medium is not occupied. Because here, station B thinks that the medium is idle here, is available, while actually station A has already started to use it. Okay. And station B will not know that A has started to use the channel until after a propagation delay. Okay. So how to resolve this? That is the key question. Well, at this point in time, at the red circle, station B knows, station A has actually started to use the channel. So here we have detected a collision. So here, station 2 detects a collision. Right? However, at this time, station A has not detected the collision yet. Station A, or station 1, detects the collision at this point in time. So here, station 1 detects the collision. Okay. So at this point in time, at the blue circle here, both stations know, okay, there has been a collision. Now they need to decide who will have priority to the channel. And okay, so what to do here? Well, one can do in many different ways, I guess, but the most natural way is that the station that's first started to transmit would get the priority. That, you know, first come, first serve. So can we figure out here the station 1? Does station 1 know if it was first or last? Or station B, does it know here if it was first and last? How can we figure this one out? Any suggestions? Suppose you're station B and you detect here. Do you know if you're first or last on the channel? How could you test for this?
Well, I guess station B knows when it sent out a message.
Exactly. So B knows when it started. This
propagation time, then you should know.
Right. Exactly. Exactly. So here's the thing. Station B knows that it started to transmit at this point and detected the collision here. So if the time difference between these two things, start of transmission and detection of collision, if this is less than t-prop, then I should release, I'm the last person on the channel, right? So station 1 started first. Station 1 does the same. It measures the difference between its starting time and the collision time, and this is now greater than t-prop. So then station 1 knows at this point, okay, there was a collision, but I have priority. Okay, so I will capture the channel. So after 2 t-prop, we know, okay, so but station 1 cannot start to transmit its frame immediately, right? It has to wait until station B has ceased to transmit its frame. So station B at this point say, okay, I'm going to release the channel, so I will stop transmitting. But that signal that leaves B at this point will reach A at this point. So at this point, sorry, there are many points now. At this point, station A knows for sure that the channel has been reserved, and it's reserved by itself. Okay. And the time it takes to do all this coordination is 2 times t-prop. 2 t-prop. And now it can start, the station 1 can start to transmit its frame, so that's the green part here. It goes over the channel, and then everything is finished at this point in time. So station 1 keeps on transmitting its frame, and it's done here. So can it then start to transmit its next reservation packet and frame here? No, it has to wait until here, because otherwise, if station 1 has a lot of frames, it will keep the channel forever. So we need to somehow let station B have a chance to capture the channel. And station B cannot start to transmit a new reservation packet signal until this point in time. So we need to be quiet for a little bit. Okay. So this sort of shows the cycle. There is some reservation time, and then there is some data transmission time, and then there is a little bit of slack time at the end in order to reset everything. And then we can start all over again. Okay. Any questions? Okay. So we have a coordination period, a data transmission period, and then a little bit of a coordination period. So can we calculate what is the efficiency of this protocol? Well, we can calculate what is the data rate that the layer above the MAC layer experiences. Well, it experiences that NF bits, which is the data frame, can be transmitted over a time, which is 1 T prop, 1 T prop, 1 TF, and another T prop. Okay, so it's NF divided by TF plus 3 T props. Okay, which means that the efficiency or the maximum load we can hope for here is the effective data rate divided by R. And the effective data rate was this NF divided by TF plus 3T prop. And then we should divide through by R. And then we get TF. Okay, so this is equal to TF. And then we have TF divided by TF plus 3 T prop divided by TF in the numerator and denominator. We get 1 plus 3A. So here we have the normalized delay bandwidth product. Okay. So when A increases, what happens to rho max? It decreases, right? So the longer the delay is between between the stations here, the less efficient this MAC protocol is. And that's more or less like a general rule. It takes time to coordinate, and the time it takes to coordinate is somehow dependent on the propagation time. Okay. Questions on this? Okay. So then let's go into some practical protocols here and see how this is solved, and then discuss a little bit about the pros and cons behind this. And let's take the simplest medium access control we can think of, and it works. It's called ALOA. So ALOA here is not an acronym. It's actually, if you know about Hawaii, right? The islands. This is like a hello phrase. And actually this protocol was developed by the University of Hawaii. If you know Hawaii, it consists of many different islands, and they wanted to communicate between these islands over a satellite link. And they wanted to then coordinate the transmissions between these, these transmitters that use the satellite link. So what is the simplest we can think of? Well, a station that has a frame to transmit, the simplest it can do is just to transmit it and then hope for the best. So that's ALOA for you, right? If I'm a station, I get a frame, I transmit this, and I wait for an acknowledgement. If the acknowledgement doesn't occur, then I know that was probably a collision, and then I wait a little bit, and then I try again. So that's the essence of this ALOA protocol. So it's in a sense very, very similar to stop and wait. So when a new frame arrives from the upper layer, okay, so remember here that we have the MAC layer, which is on top of the physical layer. So when a frame arrives from above, what do? Well, we just transmit that. Okay, and then we start a timer. And then we block the upper layer, so we don't accept any new frames from above. And then if there is no acknowledgement arriving after the timeout, then we wait a random backoff time, and then we transmit the frame again. So this is the only difference between stop and wait and ALOA in a sense, right? We have some of this waiting time before we try again. And this is actually crucial, as we will see in a second. Okay. If an acknowledgement arrives before the timeout, then we know that everything is okay, and then we can go into the ready state. That is, we start to accept new frames from the upper layer. Okay, so the frame arrival, we transmit that, we block the upper layer, we start a timeout counter. If we get an acknowledgement back, everything is okay, we can get the new frame. If the acknowledgement doesn't arrive, then we have to retransmit this, but we retransmit after a random backoff time. Okay. And without this backoff, then stations can start to collide indefinitely. So that's why we need this. So if we look at this from a timing diagram, so if we have A, B, and C are 3 stations, and if we don't have backoffs, now suppose that station A gets a frame from its upper layer at this point in time, it starts to transmit that. And suppose station C gets a frame from its upper layer at this point in time, we see that these frames would then collide at station B. And suppose station B is the recipient of these packets. So then there will be a collision here, no acknowledgements will be sent back, which means that after a timeout, station A would transmit again if there is no backoff, but station C would do the same thing. And we see that we keep on colliding here. So that's not good. So to fix this, after timeout expires, then each station draws a random delay called a backoff delay, and then wait for that amount of time before doing the retransmission. So station A has a random delay, and station B has a random delay. And with a little bit of luck, these are so different that a collision is resolved. Okay, it's no guarantee there could be a collision depending on the outcome of these random delays, but if the range of the random delays is far, I mean, yeah, so we'll talk more about this, but how to choose them so we resolve these collisions in a good way. Okay, so the backoff delay are chosen randomly in a certain interval from 0, meaning no delay, up to some maximum delay. So the maximum delay is chosen sufficiently large to make the probability of repeated collision small. Okay, so this is what we want to do. Okay, let's see. Okay, I think it's time now. I'm a little bit off with time today, as you notice. But let's take a break now for can we do it 10 minutes instead of 15, since I was late to start? Okay, great. So say 7 minutes after the hour according to that clock.